Okay, hello everyone, and welcome back to Tutte Colloquium. Today we're lucky to have Timo de Wolff. So Timo received his PhD in 2013 from Goethe University in Frankfurt. After that, he did postdocs at Saarland University and Texas A&M, and then was the head of a Noether junior research group at TU Berlin. In 2019, he joined TU Braunschweig as an associate professor, and also was elected as a member of the German National Young Academy. He works in various areas of applied algebra, including non-negativity and real algebraic geometry and polynomial optimization. And today he's going to tell us about an introduction to non-negativity and polynomial optimization. So please go ahead, Timo.
Yeah, so thanks a lot for the invitation. It's really my pleasure to be here and to speak to you tonight. Yeah, I want to give an introduction to non-negativity and polynomial optimization. And so essentially, this talk has three parts. First part is a very general introduction to the field. I'm assuming that there are a few people, at least in the audience, who have not seen this before in any other talk. So I'll try to give a general picture. And apologies for those among you who are experts and might be a little bit bored in the beginning. Then in the second part, I will focus on what we mainly do in my research group as a core topic over the last few years. And then if there's still time in the last part, I will talk about some recent result from April this year, joined with my PhD student, Janine Hoyer. Let me say, however, that if you have any questions, please interrupt, please ask questions. If I'm too fast, let me know. If I should speed up, let me know. So I'm happy to skip things if there are any questions. And we don't need to, I'm completely happy not to finish if I can answer your questions instead. Okay, with having said that, let me start with this general introduction. And let me start with a motivating example before I talk about polynomial optimization or before I talk about non-negativity. And there is a standard example everybody chooses. So I will start with a standard example, and that's the max cut problem. It's one of the key problems in theoretical computer science. In fact, there is a list of NP-complete problems by Karp with 21 problems, and that's one of them. So the setting is that we have given a finite graph G with vertices V and edges E, and we would like to solve the following problem. We would like to find a subset S of the vertices. You should be able to see my my pointer here, right? My mouse. Yeah. Okay. So we would like to find a subset S such that we maximize the number of edges that connect vertices in S and in the complement. So in other words, we would like to two-color our graph, say with red vertices and blue vertices, in a way such that we maximize the number of edges that connect vertices of different colors. And I would like to, in order to compute the maximum number of edges of this sort, I would like to formulate this as an optimization problem. And basically the name for this problem is then you think about, you cut the edges that connect vertices of different color, right? So this is why it's called max cut. So here's the construction. Let's introduce a number of variables, namely exactly as many as we have vertices. And I want to choose the variables in a way such that they can just take numbers plus and minus 1. And then I would like to solve this optimization problem. So, and I claim this is if I could solve this, then I found such a set S and I found the max cut. So let's look at this. So first of all, I'm adding this constraint here, a collection of constraints, which basically just says like I just want to allow plus minus 1 entries for my variables. And now this is the function I want to maximize. So what does it do? It sums over all edges. It sums over all edges, and then you see that it contributes with a 1 here if I have chosen two vertices xi and xj, which have different color, essentially, right? If one has a +1 and one has a -1, then I add a 1 here, and otherwise I have a 0. And so this is what I want, right? So essentially, solving this problem solves my max cut problem. And why am I showing this to you? Well, I'm showing this because if you look at this, you see all involved functions are polynomials. That's the crucial observation, right? So all involved functions here are polynomials, of course, in many variables, but all polynomials. And therefore, it is an example of a specific type of optimization problem, namely what is called a constrained polynomial optimization problem. This is what I want to introduce next. So this is the general setting. It's like a family of optimization problems. It goes as follows. We choose a family of polynomials, one polynomial f that we want to maximize or minimize depending on formulation. And then I want to collect, I want to have a collection of polynomials g1 up to gs, which serve as my constraints. And now the problem that I want to solve is I want to minimize this polynomial f given the constraints g1 up to gs, so they should all be larger or equal to 0. And I'm allowing points in Rn. Okay, so two observations to begin about this problem. Number one, this is a non-convex optimization problem, just meaning all functions are non-convex. And let me just, so if you know some optimization, then you know this is kind of like unfortunate news. And if you don't know optimization, let me just tell you this is unfortunate news. Okay, so generally, if we do optimization, we very much like convex problems. First of all, because local minima are global minima. There's just one minimum to look at. We have nice properties about duality. There is like very effective ways to solve these problems, etc., etc. So convexity is very nice and desirable, but unfortunately, we might say our problems are non-convex. And I mean, you can easily just see this, but if you just take no constraints and you take one polynomial in one variable and you just draw the graph and you see this is like in general, of course, not convex. However, this is a very general family of problems that is described here. And there are countless applications for this. So countless applications that can be written as a polynomial optimization problem. Here's a list of areas where these things appear. Of course, there are many more, but you can see here it touches various different fields. Now, don't need to read this, you can see it for yourself. Okay, it's a little bit of an unfortunate combination, maybe, right? So we would really like to have a good idea about like how to solve these problems. And now we make a first observation, right? I mean, we can say like, okay, it looks complicated, but at least everything involved is polynomial, right? So if we have polynomials, that's algebra. So maybe we can use some properties from algebra that might help us in some way, or at least allows us to say something about the structure of these problems. Here's an observation. If we look at this problem, then we can reformulate it. Solving this here is equivalent to computing the maximal constant gamma such that our polynomial f of x, if I subtract gamma, should be larger or equal to 0 for all x that live in a set G+, where G+ is the subset of Rn where all our constraints are satisfied. So really, again, if you don't immediately see it, just think about no constraints for beginning and just say like, I want to minimize a polynomial f. What does minimum mean? Well, I'm just subtracting as much of a constant until I just hit a 0 somewhere. And if I know how much I can subtract, then I know what is the value at the minimum. And so this is the role of this gamma, right? And then while we have these constraints, and so I'm not allowing all points in Rn, but I'm just allowing those points where all the constraints are satisfied. Okay, of course, this is still the same problem, but it shows that it relates solving such type of polynomial optimization problems to the question of non-negativity of polynomials, say on Rn or on these kind of like sets that are cut out by these polynomial inequalities. These are also called semi-algebraic sets. So, and this is a classical problem in real algebraic geometry to talk about non-negativity. if you look at it from an algorithmic point of view, this problem is decidable. So you could, in principle, do quantifier elimination, but it's NP hard. And of course, this doesn't go away by reformulating in any way. I mean, we have already seen max cut can be written as such a problem. That's an NP complete problem. So we have an NP hard optimization problem, or as a decision version, right? I mean, okay, let's not argue about this. But so it's certainly certainly NP hard. Okay, what can we do? The idea is now to say, well, we cannot hope that we will find just one good general approach that will solve all of these problems, but or we should not hope maybe, but instead the idea is to find something that's called a certificate of non-negativity. What is this? So we want to find other conditions that would imply non-negativity. So when I say other conditions, I mean other conditions on the polynomials that we investigate, that should imply non-negativity, that should be somewhat easier to check than non-negativity itself, because we just established that this is hard, and that should often be satisfied for many polynomials. And then for the moment, in order to get a little bit of an idea about this, let's completely forget about these constraints. Let's just say I want to just minimize one polynomial in n variables, and I would like then to say like, okay, this is equivalent to like deciding non-negativity, and this is still hard. So what I would like to have is some condition that implies non-negativity, is easier to check than non-negativity itself, and is often satisfied, whatever often means. Here's a classical example for something that points in this direction. And this is called a sum of squares. A sum of squares just means that my polynomial can be written as a sum of other polynomials that are squared. So it's like literally meaning what it sounds like. And you see, if I would know that such a decomposition exists, then I would immediately know that my polynomial is non-negative. So it's like just the first condition of my three, let's say, desirables that I have among a certificate of non-negativity. Okay, so maybe this is a good candidate for a certificate of non-negativity. Now the question is, how do I compute this, right? It should be easier to test than non-negativity itself. And for that, let's look at convex optimization problems. So you remember, I told you a few slides ago that convex optimization problems are the problems that we like because there are effective methods for solving them. So if I say testing for non-negativity, or like subtracting a maximum gamma such that I am, like to phrase it as an optimization problem, subtracting a maximum gamma such that I am the sum of squares, that I hope that I can detect this by solving an optimization problem that's easier than to subtract the maximum gamma to decide non-negativity. And ideally easier certainly would be if I had a convex optimization problem. Okay, so let's look at some convex optimization problems. The one convex optimization problem that probably most of you have seen or at least heard about is a linear program. Let me just quickly recall how a linear program looks like. And of course, first of all, you get convexity in this because all involved functions are linear, and linear functions are convex. Okay, precisely how do these problems look like? You choose a matrix and you choose a vector for a right-hand side of equations, and then you choose another vector that is basically used to form the target function. And then the problem that we solve is we minimize a linear form that is basically induced by the C. And then we add a bunch of constraints, which are here I just write shortly as in a compact way as a multiplying a matrix with this vector X and then being smaller or equal than some vector. And basically every row of this gives me one linear condition to satisfy. In total, this means I have, well, row many, m many of these linear conditions. So this means I cut out, like for every condition, I cut out a half space. And this means overall, the feasible region that I would get is a polyhedron. Some region in Rn that's cut out by finitely many of these linear inequalities. Okay. These problems can be solved effectively. So the standard way to solve this is using a simplex method. And the problem is convex. Everything is linear, so it's in particular convex. And convex problems are efficiently solvable. I mean, efficiently solvable, that in a numerical way, up to an epsilon error, and it's in the size of the input, etc. But I don't want to talk about too much about the complexity, but just take it as a linear this linear program as an example of something in this general realm of convex optimization problems. And we should just think about this. This is something that we can effectively solve. Okay, so we might hope that we use linear programs to detect sums of squares, but it's too restricted for what we need. So instead, let's look at something that's a little bit more general. And for that, we want to use something that's called semi-definite programming. Okay, let me introduce that. So we, as a starting space, we consider the space of real symmetric n times n matrices. And recall that a matrix is called positive semi-definite if this property here holds for all x and Rn. So I'm taking any vector x and Rn, and I'm computing x transpose times a times x, and that should be non-negative for all x and Rn. If a symmetric matrix has this property for all x and Rn, it's called positive semi-definite. Equivalently, one can show equivalently you can request that all eigenvalues are non-negative of this matrix. Okay, now we can take as a subset of the real symmetric matrices the set of all positive semi-definite matrices, and in fact this is a convex cone in the space of real symmetric matrices. And now we can formulate an optimization problem over that. And let me first write it down here for you. This is called a semi-definite optimization problem. And if you first look at this, this first part, then it looks almost like a linear program. Okay, you have an equality condition, but there's a bunch of equivalent formulation also for LPs. I mean, it does not really make a difference if you have an inequality or an equality here. So that's not changing anything. And here you might say, what does this mean? Well, this is like a standard inner product on matrices. So essentially it works just like an inner product on vectors. If you just think about the matrix as being a long vector, right, then it works the same way. So essentially, up to this point here, this looks just like a maybe very fancy way of writing down a linear program, and nothing has really changed. But the difference happens down here with this additional condition. So I'm on top of these conditions here, I'm requesting that my matrix X that contains my variables, that this is a positive semi-definite matrix. And that is now changing something. It's really, this problem is more general. The feasible region of such a problem is called a spectrohedron. You might have heard the term. So if not, then just take it as a generalization of a polyhedron. So every polyhedron is also a spectrohedron, but not vice versa. And the good thing still is this is still a convex problem. So it's still a convex problem, and it's so solvable in general with the same, in at least from a complexity perspective. Again, polynomial time up to epsilon error, etc. in the size of the input, for example, via something that's called interior point method. So again, we can hope that there's a good way of solving these things. And now it turns out that these semi-definite programs are exactly what we need in order to detect sums of squares. As I said, it generalizes LPs. Okay, let's see how it goes, because I mean, at least when I first saw this, and I think saw it the second time, then I thought like, okay, that's I understand maybe the definition of an SDP, but I don't see how it's related to sums of squares. And for this, you need a particular theorem. And in order to formulate it, let's introduce a little bit more of notation. So first of all, I want to investigate polynomials in n variables, right? And I want to like decide non-negativity, and maybe I want to have sums of squares as a certificate. So what I would first do is I would just say, let me artificially restrict the total degree of the polynomial. By total degree, I always mean like I take any exponent vector that's like for a vector of length n, if I have n variables, right? And I just sum up the entries. And what I want to do is I want to say that I don't want to consider any polynomials that have a total degree higher than 2D. This has the advantage that if I consider this as a vector space, it's a finite dimensional vector space. It's much more convenient than an infinite dimensional vector space. Okay, So let's work on this vector space of real n-variate polynomials of degree at most 2D. And now I want to consider the vector MD of all monomials in n variables that have total degree at most D in any ordering that you like, say lexicographic ordering, right? So I'm writing down all monomials in n variables such that the total degree is at most D in any order, and I put them in a very long vector, okay? And then there is a theorem which is called the Gram matrix method that, to the best of my knowledge, was first in this paper by Powers and Werman. Otherwise, maybe people can correct me later if there was an earlier instance of this, which says the following. It says, if you have a polynomial in this space, so it's a n-variate polynomial of degree at most 2D, then this polynomial is a sum of squares if and only if there exists a positive semi-definite matrix G such that I can write F as MD transpose times G times MD, where MD is this vector of all of these monomials. Okay, first convince yourself. So this is a symmetric matrix. Okay, it has this positive semi-definite condition. Forget about this for a second. This is a matrix, so it contains numbers in there, right? And this is a vector where every entry contains a monomial. So I'm multiplying monomials from the left and from the right. And every monomial here has total degree at most D. And so the same is true here. So, and if I multiply this out, I will always at most multiply two monomials with each other for every sort of entry that I get. So in total, I get a sum of monomials. I get a polynomial, and the total degree that I get is at most D plus D. So it's at most 2D. So indeed, I get back a polynomial in this space. And then, of course, one needs to work and see that really this positive semi-definiteness is the right condition to put on this matrix, to find such a matrix. Of course, still you have to find it, right? I mean, it is just putting a relation between sums of squares and positive semi-definite matrices. But the key observation was, I mean, and this was not done in this paper, this was done later, or a little bit after 2000, so like by Perillo in 2003, and around the same time independently by Lasea using another language, that this can be checked using semi-definite program. I mean, it's not so surprising, right? It's a positive semi-definite matrices, but the connection was not made at the time. And at this time, Pablo made this connection. And so people realized suddenly, oh, we can really use semi-definite programs to compute sums of square decompositions. And that was a good starting point to basically this entire field, because remember, semi-definite programs are convex programs. There's effective ways to use them. Okay, let's now look at the next question. See, like, is every non-negative polynomial a sum of squares? You might hope, right? I mean, maybe every non-negative polynomial is a sum of squares. But this is not, in fact, a new question. That's an old question, and by old I mean 19th century question, which was already investigated by Hilbert, and Hilbert made the following, proved the following very fundamental theorem. So he said, like, he also looks at these spaces of polynomials where you have a degree restriction, and n is the number of variables. And then inside of this vector space of polynomials, he considers the set of non-negative polynomials, let's call this Pn2D, and a set of sums of squares, sigma n2D. And he proves that these two sets, in fact, they are not just sets, they are convex cones in this vector space. They're equal if and only if you're in one of three special cases. Namely, if you have univariate polynomials or polynomials of degree 2, or this one special case, two polynomials in two variables of degree 4. And in all other cases, there exist polynomials that are non-negative but not sums of squares. He did not do it in a constructive way. This was an existential proof, very, very beautiful proof using something that's called the Cayley-Bacharach theorem. But here's an explicit example. That's like the first known example in the literature. It's called the Motzkin polynomial. Let me just give it to you as an example for now. This is a non-negative polynomial, which is not a sum of squares. Of course, it's not obvious. We will later come back to this. But this is a non-negative polynomial, which is not a sum of squares. And you can see it's just outside of this Hilbert case. It has two variables, degree 6. So it's just outside of this. Another quick historical note, this theorem here led to one of Hilbert's problems, namely the 17th one, asking, okay, if I cannot write every non-negative polynomial as a sum of squares of polynomials, can I write it as a sum of squares of rational functions? And indeed, one can. This was proven by Artin almost 100 years ago now. Yeah, so was, I think, the second of Hilbert's problems that was solved. One more recent observation on the theoretical side. Now, you might hope that still something like the Motzkin polynomial is very much the exception, because it's like hard to find counterexamples, and like in these cases, you even have equality. But there is a theory by Greg Bleckerman from 2006, which very roughly says, if you fix the degree in these spaces, and the degree is at least 4, and now you let n go to infinity, and you compare these cones in a particular way, you have to introduce a measure, etc., to do this, then if n goes to infinity, almost every non-negative polynomial is not a sum of squares. So like asymptotically, this property, which is like almost always satisfied for the non-negative polynomials in these small cases, becomes very, very rare. That's maybe like the takeaway. Okay, now we might say, well, this is all theory. This is like the correct picture we have in mind. There's 2 convex cones. Here, in general, this SOS cone is a strict subset out of the non-negativity cone. These cones are convex. They are not polyhedral. They are way more complicated than that. And they live for every n and in 2D, we have this structure. Okay, and now you might say, well, but I care about optimization. I want to know how well these things really work in practice. I want to solve things like max cut, right? In practice, I want to know how this works. And then the good news is there is a lot of things that you can do. So first of all, if you have such a constrained polynomial optimization problem, not only for the cases we discussed here about just minimizing a polynomial, also for the cases where you have constraints, this ansatz of SOS/SDP works well. So you can exploit something that's called the Positivstellensatz, which I don't want to talk about today, in order to get the constraints on board. And then there is some very nice approach that's called Lasserre relaxation, which gives you often, and under mild conditions, converging hierarchy of lower bounds of non-negativity to solve constrained polynomial optimization problems. Another good news is there is software and there is solvers. So you don't need to do all of this by hand. For SDP, there is solvers where you can hand the problems to, and then you might say, well, but it's still painful. I don't want to write down the SDP. If I just want to write down my constrained polynomial optimization problem, that's also okay. There is software that translates this problem into an SDP, gives it to the solver, and hopefully the solver will solve it. So that's all the good things. There is something negative though. Because I mean, still remember, we are dealing with at least some NP-complete problems. And the main negative observation is the following. That's the size of the gram matrices that are involved. Namely, if I have a gram matrix that is handling a vector of monomials of length or of MD, then this vector is of length n plus d choose d. So this means these matrices we have to put in our SDP are growing exponentially in n and d. So this means the SDP is a polynomial time algorithm, but in the sense, at least if both n and d grow, we have an exponentially growing input size. And that is mainly like the question or the problem well, in the end, we have to solve. And so it's the reason why all of this remains very challenging from a computational point of view. Okay, so now, of course, there's several things you can do. And next to just improving software and solvers. And one possible improvement that has been done and where there is a lot of improvement also recently is to exploit structure of the problem that you have at hand. So what I described to you with this gram matrix method is, of course, like very naive, right? I have put zero information about my polynomial that I have at hand or my constraints into this. I just wrote down this matrix and then I said like, okay, let's solve some kind of SDP to find me this gram matrix. But often you can exploit the structure. So often you will have sparse systems, for example, you might have symmetry, other things like that. One can exploit this. This was done already years ago by Pablo and collaborators. And then let me here mention this recent work by Lacerma, Grand and Wang, which really leads to quite impressive speedups in what you can compute. So, however, this is not what we are doing. And now I want to slowly converge to part number 2. What we are doing is we wanted to introduce new ways to certify non-negativity. And this is what we do mainly in my group. And this is what I want to talk about now. In the second part, however, maybe let me quickly pause and see whether there are urgent questions now that I should address. Okay, so then let me go on. Our idea was to say, well, I mean, maybe there is another meaningful way to introduce a certificate of non-negativity. So see, one can use sums of squares, but of course, they seem to be very natural to use, but maybe they're not the only way to do it. And the idea that we had was to use these sums of non-negative circuits, and the building block is what we call a circuit polynomial, which I want to introduce now. And we here is Zadig Iliman and myself, and this was 2014. So it's already a while ago. This first definition is a little bit technical, but bear with me. I will talk through the conditions that come now and show you what it means. So a circuit polynomial is a particular type of sparse polynomial. It has, well, let's say we are in n variables. It has r plus too many terms, and it should satisfy 3 conditions. The first condition is that we want to investigate the Newton polytope of this thing. The Newton polytope is the polytope that I obtain by taking the convex hull of the exponents. So it's r plus too many exponents that I have because I have r plus too many terms. And I want that this Newton polytope is an r simplex. And if r is confusing you, then just think as r being equal to n. So essentially what it says is like I'm living, the Newton polytope is an r-dimensional polytope, and I have r plus too many terms. It's so I have an r simplex. So it's like, it's the kind of the easiest structure I can have in terms of a Newton polytope. And in terms of the support, I have just one term more beyond looking at something that is completely trivial. And this one extra term that I have should be the term with exponent beta, and the terms with exponents alpha 0 up to alpha r should be the vertices of this simplex, r plus 1 many. Okay, what about this beta? That's the second condition. I want that the beta, this exponent, lives in the strict interior of the simplex. And here is a little bit of a fancy way of writing this, and you will see in the next slide why I'm writing it this way. So what I'm here saying is, if I express beta in barycentric coordinates with respect to the vertices alpha I, then I want that this well, should be a convex combination, really, right? So it's and all the coefficients should be strictly positive. Why am I imposing this second condition? Well, essentially because every other case can be restricted to this one. So it's not really complicating things. It's just the only interesting case. And the third condition that I have is that all the coefficients, except for the ones that correspond to this interior term, beta, all the coefficients bj, they should be strictly positive, and the exponents should just have even entries. And now you might say, well, this is very special, but in fact, this is a condition, this is a necessary condition for any polynomial that I want to be non-negative, or that I hope for to be non-negative. Okay, so let me say this again. If you have any polynomial f, and the question is, could this be a polynomial that's non-negative on r to the n? Then this condition 3 is a necessary condition for all vertices of the Newton polytope and the corresponding coefficients. Will not show this now, but you can think about this later after, well, dinner or something like this. So it's a nice little exercise. We call this a circuit polynomial because the support set is a circuit, a specific type of circuit. And now you might say, well, this looks very technical and very special. Is there even an example for this thing? And there is an example, namely here, the easiest example that is not very boring is this Motzkin polynomial that you have already seen. Okay, Why would we investigate these polynomials? We do that because it is very easy, in contrast to the general case, to decide non-negativity of a circuit polynomial. I claim all that you need to decide non-negativity of a circuit polynomial is this number. It's called as the circuit number. And first observe that this number can be very easily computed. Why is that? Well, first of all, what does it involve? It involves the coefficients of the polynomial, well, all but one coefficient, all but the coefficient of the interior term. Okay, this is given. And then it involves these values lambda here. And recall, lambda are the barycentric coordinates of the interior term. So this is essentially solving a system of linear equations, right, to get these lambda. So this is, at worst case, linear programming to compute this number. Okay, why is it enough to have this number? Well, because the first theorem that we ever proved in the first paper we ever wrote about this thing was that if you have such a circuit polynomial, then this is non-negative if and only if the coefficient of this interior term is bounded in absolute value by the circuit number. And that's an if and only if, unless you have a sum of monomial squares. But this is completely trivial if you have this. If every term is a square with positive coefficients, you're obviously non-negative and you don't need to go on anymore. So you can just like put this aside, and then this is really the condition you're looking for. Okay, I need to give some credit. This was known in special instances. This was known when the coefficients are just the barycentric coordinates. Then this is called an Agee form. This was shown by Bruce Resnick already in 1989. And then there are some other special cases that was known before. So here's a result by Fidalgo and Kovacic for certain simplices. Okay, now let me give you a quick idea about why this is true, about the proof. I know three ways to prove this. You can use what is called the AMGM inequality to prove this. You can do a brute force computation using basically calculus 2. This is what we did in the first paper. And you can use something algebraic that's called A discriminants that I don't want to talk about now. Let me use the AMGM inequality. It's a very classical inequality. It states the following. But it says this inequality is true here. And what is the condition? Well, the condition is, I mean, or it's one way to state this, is to say, I take any non-negative number, collection of non-negative numbers Tj, and I take any collection of non-negative numbers lambda j such that these lambda j sum up to 1. And then this inequality holds. Okay, classically, no. Now, we can use this to show non-negativity of circuit polynomials, or to show that this is equivalent to having the circuit number. So first, you make an observation that is essentially enough to consider non-negativity on the positive orthon, because, well, there is just one term that can ever be negative. This interior term, because everything else has a positive coefficient and exponents that are just have even entries, so they are all positive anyway. So it's enough to be on the positive orthon. And then you start with a special case. And the special case is this case that was done by Bruce Resnick, where you have you choose your coefficients equal to these barycentric coordinates. Okay. Then you first observe that in this special case, the circuit number is always 1. So why is this? Well, because recall that the circuit number was defined in this way. And if my coefficients bj are equal to lambda j, then this entire thing is 1. We don't need to worry about it. It's just 1. Okay, what does it mean now if we go on further? We want to use this AMGM inequality. We choose for the tj's in this inequality, we just put in our monomials that we have, x to the alpha j. And then we make a straightforward computation. So my polynomial bj x to the alpha j. So I write this in notation of AMGM inequality. I apply the inequality. I translate this back. And then I have a product of all the x to the alpha j. And I realize this is the sum of all of the alpha j's. And then there's a typo. This should be alpha j to the power of lambda j. And then I have a sum of lambda j alpha j, and this gives me beta. And I can multiply with the circuit number theta f because it is 1. And this is exactly the statement that I wanted to have. So I've shown that this part is largely equal than this part. Okay, and now once I have that, I can go to the general case where I have arbitrary coefficients, and essentially I just make a smarter choice for these TJs. And then with a similar argumentation, you end up with an expression like this. And then you realize that by applying the AMGM inequality, that the condition that you need to satisfy is exactly that, which is the proof, or finishing the proof of the theory. Okay, so now you might say, well, that's nice that you have these circuit polynomials, but maybe there are all sums of squares, right? And then it's not very exciting because we could just do sums of squares. Now, I already told you that the Motzkin polynomial is not a sum of squares, but I did not prove it. Was there a question? Yeah, please.
Why can you restrict to the positive orthont when you're...
Okay, yes, good. Let me just go back to the definition. Yes, so this is the polynomial we have at hand, right? And we have this third condition, which says that every of these coefficients here is positive, and every entry of an exponent here is even. So this means no matter what signs a vector x has, these will always be positive terms, right? So
Okay.
so we can assume that this coefficient here is negative, and then we have one negative term on the positive orthon. That's the orthon we want to restrict to. So what can happen in one of the other orthons? Either if I just switch signs of some point x were evaluated, for some xi's, then either everything just looks exactly the same, like on the positive orthon, or I just have a polynomial which just has strictly positive terms.
Okay.
So the only case really that is interesting that I have to investigate is on the positive orthon.
Thanks.
Yeah, you're welcome. Okay, so you might, coming back to this question about sums of squares, right? So you might say, well, is every circuit polynomial a sum of squares? And it turns out that the answer is no. But there is a condition to check. And the nice part about this is that this is a purely combinatorial condition. Normally, if I have a non-negative polynomial, it depends on the support and it depends on the coefficients, whether this polynomial is a sum of squares, yes or no. But for circuit polynomials, it's not true. If I have a non-negative circuit polynomial, it just depends on the exponents, on the support alone, whether this is a sum of squares, yes or no. And for that, we need to define something, an object that's called the maximal mediated set that was introduced by Bruce Resnick. So it's a little bit of a technical and a little bit horrible definition. But again, if it's getting a little bit too complicated, or if you get lost in notation, just wait for a moment. We'll jointly do an example. Okay, let's do the definition. So I'm starting with a set of lattice points, and you can think about them as the vertices of our Newton polytope. So I have an n simplex, right? And these are my exponents of the positive terms. And now I consider a subset of lattice points, and I call this delta mediated if, first of all, my points delta are contained in this set n. And I have the following conditions. Whenever I have a point P that belongs to the set M and is not one of these points delta, then there have to exist two other even points, just with even entries, that also belong to M, such that my point P is the midpoint of these two other points. And they need to be distinct. So it means every point that I have in such a delta mediated set either belongs to delta itself, or it's the midpoint of two other all even points that also belong to the set. And then we call a set delta star a maximal delta mediated set if it is delta mediated and it contains every other delta mediated set that I have on the lattice points that are contained in delta. This was introduced by Bruce Resnick, and he showed that such a maximally delta mediated set always exists, and it's always unique. And where is it contained? Well, at most, it is just the set of all lattice points that are in the simplex that's given by the convex hull of my set delta. And what is the lowest that I can get? Well, I always have the vertices of my simplex by definition, and they just have even entries. So I will always have at least the vertices and the midpoint at every edge. And this is what is here described as a delta. And in general, the delta mediated set is something in between. So in fact, what Bruce showed more precisely, or what he conjectured, he showed in some examples, that in dimension 2, these are the only two cases that can happen, but in dimension 3 and higher, you have sets in between. And he used this delta mediated set for the special case of agiforms to show that they are not always sums of squares. And in fact, we generalized his argument to circuit polynomials, deciding when they are sums of squares. Namely, we showed when we have a non-negative circuit polynomial, then this thing is a sum of squares if and only if this particular inner term, this distinguished inner term that corresponds to the coefficient that can have a negative value, this thing needs to belong to the maximal delta mediated set with respect to the Newton polytope of this polynomial. Or again, you can have a sum of monomial squares, which is the special case that we discussed already before. Okay. There is more to say. In a more recent work, we showed that we investigated these delta mediated sets more, and we showed in particular that you can, if you have two simplices, then the corresponding delta mediated sets are isomorphic if and only if you, essentially these simplices span the same lattice in the way that you can always move them in a way that one of the lattice points is the origin, and then you consider all the other vertices as basically basis vectors of a lattice, and then you look at the lattice that you span. Okay, so let me show you.
Question. Sorry.
Yeah, go ahead, please.
The maximal delta mediated set is not uniquely defined, right? So in these statements, you're actually saying that there exists. Is that right?
There exists, yeah, but in fact, it is. Well, it is it is unique and it is defined in this way. Okay. And there's also an algorithm to compute it. So this is why I'm said, if you're a little bit lost in this definition, don't worry. I will show you an algorithm now to compute it.
Okay, thanks.
And that's, I think, easier to grasp. Let's in fact look at the Motzkin polynomial. Let's prove together, maybe as a well, probably already final point, that the Motzkin polynomial is a non-negative polynomial which is not a sum of squares. And let's use circuit polynomials and maximal mediated sets. Okay, this was the Motzkin polynomial, right? It was a polynomial in two variables of degree 6. Observe it is a circuit polynomial. Why is it a circuit polynomial? Well, first of all, we said a circuit polynomial should always have two more terms than the dimension of its Newton polytope. What's the Newton polytope? Well, this term 1 here just has exponent 0, 0, right? So we have exponent vectors 0, 0, 2, 4, 4, 2, and 2, 2. The Newton polytope is a triangle with vertices 4, 2, 2, 4, and 0, 0. And this is an interior point. Let's stick here for a second. So it's a triangle. It has dimension 2. It has 4 terms. Newton polytope. A triangle is a 2 simplex. So this is also satisfied. This is an interior point. This is a point in the strict interior. This was the second condition to be satisfied. And then you see that all the exponent vectors of the term which does not attain a negative value just has even entries, and the coefficients are positive. Third condition. So it's also satisfied. So it's indeed a circuit polynomial. Okay, let's check whether it's non-negative. What do we have to do? Well, we have to compute the circuit number, right? So first of all, we compute the barycentric coordinates of the interior term with respect to the 3 vertices of our triangle. And then we see the barycentric coordinates are easy in this case. It's just like 1/3 in all for lambda 0, lambda 1, lambda 3. And this is the correct linear condition that we want to satisfy. Okay, once we have these, we can compute the circuit number. Recall that this was the circuit number to look at. And now we put everything inside. So the BJs, this is easy. They are all coefficients 1. So these are just a bunch of 1s. And all the lambda j's are 1/3. So this is the condition that we have to satisfy. And if you just compute this, you see like, well, it's actually, you have a product of 3s to the power 1/3, and you have 3 of them. So it's 3 to the 3 to the power of 1 over 3 to the power of 3. So in other words, it's 3. So the circuit number is 3. And what did you have to do with respect to the coefficient, to the coefficient of the interior term? You have to take the absolute value of this thing and you have to compare it to this number. And you see, well, it had to be smaller or equal, but in fact it is equal. So what this shows, according to the first theorem that we have learned, is this is indeed a non-negative polynomial. And in fact, since this is satisfied with equality, it is a non-negative polynomial with zeros. And that's easy to see. It has a 0, for example, at the point 1, 1. Okay, finally, why is this thing not a sum of squares? Let's compute the delta mediated set of this.
Timo,
and
if you could finish in 5 minutes, that would leave some time for questions.
Yes. I will skip the last part and I will just show you this and then we can go for questions. So let's compute this thing. And what is the algorithm that you have to follow? So the algorithm says you start with all lattice points in the Newton polytope of your polynomial. So this is all lattice points. And now I look at the subset of all points which just have even entries, which are these ones. And now I look among the remaining points that are look at all the points that are not a vertex, because the vertices, remember, belong always to the max mediated set. So I look at all the points and I'm asking which of these points are the midpoints of 2 other points which just have even entries. Okay, these 6 points that I'm just adding here are midpoints of 2 points which just have even entries. So everyone I can write as the midpoint of 2 of the green points. But there is 1 point missing, namely this middle point here in itself. This point is not a vertex, and it's not the midpoint of 2 other points which just have even entries. So I will throw this point away because it would violate one of the second condition in the definition of this delta mediated set. So I'm throwing this away, and now I'm running into a loop and I'm continuing the argument that I have. I'm looking at all the points which are just have even entries, that are these, the ones are remaining. And among all the points that I have that are not vertices now, I'm asking which ones are now midpoints of the points which just have even entries. It's just these 3 now, right? Because the middle point, I've thrown the middle point away. So these points, these 3 points that I had before here, I cannot write anymore as the midpoint of 2 of the green points. So I also have to throw these ones away because I cannot write them as the midpoint of 2 all even points. And then this thing becomes stationary, right? So now I'm just ending up with points which are either vertices or midpoints of 2 all even points. So this thing is the delta mediated set, according to this algorithm that we used, that Bruce used. And now the second theorem says, now you have to look whether the exponent delta belongs to this set. But it doesn't, because the exponent delta is the point 2, 2. It's like here in the interior. Actually, no point in the interior belongs to the maximum delta mediated set. So therefore, since this point does not belong to the set, this polynomial that we have looked at, this Motzkin polynomial, is not a sum of squares. Okay, final thing that I will tell is you can now, because circuit polynomials in itself are not very interesting, but you can look at sums of these non-negative circuit polynomials and write, this is just every polynomial that I can write as a sum of a finite sum of non-negative circuit polynomials. And these things form a convex cone again. And this cone is, well, it's not contained in the SOS cone. We have just shown this. And this cone is full dimensional. And this means in total, we have found a new certificate of non-negativity, which is independent of sums of squares. And at that point, I will finish before going completely over time. And I'm sorry that I had no time to talk about this more recent work, but please feel free to ask questions. Thanks a lot.
Great, let's thank you.
Yep.
We have time for a few quick questions. Yep, Tim?
So, thank you for the talk. Is there a convex programming hierarchy associated with this?
Yes, there is. So Yeah, I mean, that's of course, I mean, I just said at the end, right? I mean, we have found a certificate of non-negativity, and as you point out here correctly, it seems like I've omitted something. Namely, we said like it should be able to compute these things easier. So what I would have to do, let me just get back, is if I am here, if you give me a polynomial f, I should be able to find a decomposition into non-negative circuit polynomials. And it's, of course, I mean, it's easy maybe to check if I already have this, that these things are non-negative with what I showed you, but the question is how to compute it. And one can do that using another type of convex optimization problem. And this is called, in the general way that you have to use, it's called relative entropy programming. This is maybe not so well known. Maybe you know some more special instance of that. This is called geometric programming. In some more special cases, you can use that. But in any way, so you can think about these relative entropy programs as a generalization of geometric programming. And they are convex optimization problems. They are solvers in order to solve them. And there is a formulation of finding such a decomposition using these relative entropy programs. And this also works with constraints. So of course, there is like a lot more work you need to do in order to incorporate constraints in general, but you can do it. And you can use relative entropy programs to find these decompositions.
Thanks. Other questions? So I know you focus a lot on applications of these kinds of techniques. So have you been able to use circuit polynomials in specific applications?
Yes, we did. So one thing that we did, in fact, there is a paper, basically a follow-up paper on what we did appearing on the archive on Monday, hopefully. So what we did in this first paper was we applied these problems from chemical reaction networks. So the problem there is a specific type of network. So this was joint work with Oğuzhan Yörük, who was a PhD student in my group, and then with Elisenda Feliu and Nidi Kainsa, who were, I mean, Elisenda is one of the experts working on these chemical reaction networks from an algebraic perspective, and Nidi is a postdoc at Brown and who also works on this. And so they had a specific type of network, which is called two-phosphorylation. It's a particular, I mean, I'm not an expert, of course. It's modulating obviously certain important chemical reactions. I don't know, right? I mean, I don't want to say anything wrong, but and it's also kind of from this algebraic perspective. I learned from Elisenda that it's like kind of like a standard model to consider, like to test certain properties. So, okay, a chemical reaction, you can think about this as a dynamical system, and you would like to see so it depends on certain reaction rates, right? So it's like basically the reactions, the total reaction is like written down, but then for specific parts, you have reaction rates you can choose. You can think about, if you have one of these networks, you have a configuration space basically of these things, depending on the reaction rates, which are just positive real numbers. And then the reaction goes, right, and stuff can happen. And in particular, what can occur is that you can have one or more stable situations into that you run. And this then is also called mono or multi-stationarity. So depending on whether you have one or more of these like stable conditions in that you run. And then it turns out you can translate these things into questions of non-negativity, again, which is not my field. Like I just learned this from Elisenda. But what it turns out is this is like tricky to show non-negativity of these polynomials, because the polynomials in their coefficients depend on the reaction rates that you don't know. So essentially you would like to decide non-negativity for a symbolic polynomial where the coefficients are symbolically given in the reaction rates. And we would like to give bounds on non-negativity depending on the reaction rates that you choose. And it turns out that you can use circuit polynomials to do that. In contrast, for example, for sums of squares, it's not clear how to do it. But for circuit polynomials, it goes forward because this circuit number is a symbolic condition that depends on the coefficients. So you can write this down. You can make a decomposition into circuits that was not too complicated in this case, and then we could come up with good bounds for mono versus multi-stationarity. And basically in this paper that's appearing on Monday, we generalize this to like from 2 to n phosphorylation. I mean, not everything generalizes, but parts of this approach. And I mean, without giving it too long of an answer, we have also applied this to problems in theoretical computer science and using independent methods.
Oh, very interesting. I think we're out of time, so let's thank Timo again.
Thanks a lot for coming and for listening.
So